The real topic is how to solve inhomogeneous systems, but the subtext is what I wrote on the board. I think you'll see that matrices, really thinking in terms of matrices, makes certain things a lot easier than they would be otherwise. And I hope to give you a couple of examples of that today in connection with solving inhomogeneous systems. Now, there is a little problem. We have to have a little bit of theory ahead of time before that, which I thought, rather than interrupt the presentation as I give you, try to talk about the inhomogeneous systems, it would be better to put the little theory in the beginning. I think you'll find it harmless, and about half of it you know already. So, the theory I'm talking about is, in general, the theory of the systems x prime equal ax. I'll just state it when n is equal to 2, a 2 by 2 system like we've had up till now. It's also true for n by n. It's just a little more tedious to write out and to give the definitions. So here's a little 2 by 2 system. It's homogeneous. There's no zeros. And it's not necessary to assume this, but since the matrix is going to be constant until the end of the term, I think let's assume it and not go for a spurious generality. So constant matrices like you'll have on your homework. Now, there are two theorems, or maybe three, that I want you to know, that you need to know in order to understand what's going on. The first one, fortunately, is already in your bloodstream, I hope. Let's call it Theorem A. It's simply the one which says that the general solution to the system, that system I wrote on the board, the 2 by 2 system, is what you know it to be, namely, from all the examples that you've calculated. It's a linear combination with arbitrary constants for the coefficients of two solutions. In other words, to solve it, to find the general solution, you put all your energy into finding two independent solutions, and then as soon as you've found them, the general one is gotten by combining those with arbitrary constants. So the only thing to specify is what the x1 and the x2 are. So where, I guess, would be the right word to use, where x1 and x2 are two solutions, but neither must be a constant multiple of the other. So that's the only thing I want to stress. They have to be independent, or as it's better to say, linearly independent. Are two linearly independent solutions. And department of fuller explanation, i.e., neither is a constant multiple of the other. That's what it means to be linearly independent. Now, this theorem, I'm not going to prove it. I'm just going to say that the proof is a lot like the one for second-order equations. It has an easy part and a hard part. The easy part is to show that all of these guys are solutions. And in fact, that's almost self-evident by looking at the equation. In other words, for example, if x1 and x2 each of those solve that equation, so does their sum, because when you plug it in, you differentiate the sum by differentiating each term and adding. And here, a times x1 plus x2 is ax1 plus ax2. In other words, it's just you using the linearity and the superposition principle. So it's easy to show that all of these, maybe I better say that, actually write something down instead of just talking. So easy that all these are solutions. Every one of those guys, regardless of what C1 and C2 is a solution. That's linearity, if I use that buzzword, plus the superposition principle, that the sum of two solutions is a solution. hard. The hard thing is not to show that these are solutions, but to show that these are all the solutions, that there are no other solutions. No matter how you do that, it's hard. So the hard thing is that there are no other solutions. These are all. Now, you can sort of hand wave and say, yeah, well, it's got two arbitrary constants in it. That's sort of a rough and ready reason, but it's not considered adequate by mathematicians. And in fact, I could go into a song and dance as to just why it's inadequate, but we got other things to do. Bigger fish to fry, as they say. Okay, so let's fry a fish. No, we have another theorem first. So this one, it's mostly the words that I'm interested in. Once again, we got our old friend the Wronskian back. A Wronskian. The Wronskian of what? Of two solutions. So it's the Wronskian of the solution x1 and x2. They don't, by the way, have to be independent, just two solutions of the system. And what is it? The answer is, hey, didn't we already have a Wronskian? Yeah. Forget about that one for the moment. I'll postpone it for a minute. This is a determinant, just like the old one was. And what, sorry. X1. This could be a great lecture. X1, X2. Now, what is this? Okay, X1 is a column vector, right? X2 is a column vector, two things in it. So together they make a square matrix, and this means it's determinant. So it's the determinant of this. It's a determinant, in other words, of a square matrix, and that's what it is. I'll change this equality to indicate it's a definition. I'll put the colon there, which is what you add, to indicate that this is only equal because I say so. It's a definition, in other words. Now, there is a connection between this and the earlier Wronskian, which I unfortunately can't explain to you because you're going to explain it to me. I gave it to you as part one homework problem, and be sure you do it. And if you can't remember what the old Wronskian is, please look it up in the book. Don't look it up in the solution to the problem, okay? So if you do that, you'll learn something, and then you'll see how, in a certain sense, this is a more general definition than I gave you before. The one I gave you before is, in a certain sense, a special case of it. Okay, now, that's just a definition. There is a theorem, and the theorem is going to look just like the one we had for second-order equations, if you can remember back that far. The theorem is that if these are two solutions, there are only two possibilities for the Wronskian. So either or. Either the Wronskian is. Now, see the Wronskian, these are functions, the column vector is solution, so those are functions of the variable t, so are these. So the Wronskian as a whole is a function of t, is a function of the independent variable t, after you've calculated out that determinant. So the answer is that Wronskian, I'll write it now this way to indicate, bring to the fore that it's a function of t. Either it's equal to, well, that's not the way to write it. Either the Wronskian is, so one possibility is identically zero. That's zero for all values of t, in other words. And this happens if x1 and x2 are not linearly independent. Usually people just say dependent and hope they're interpreted correctly, are dependent. But since I didn't explain what dependent means, I'll say it. Not linearly independent. I know that's horrible. But but nobody's figured out another way to say it. So that's one possibility, or the opposite of this is never zero for any t. I mean, a normal function is 0 here and there, and the rest of the time not 0. Well, not this Wronskian. You only got two choices. Either it's 0 all the time, or it's never 0. It's like the function e to the t, in other words, an exponential which is never 0, always positive, never 0. Or a constant. It could be a constant. Anyway, it has to be a function which is never 0. And this happens if, in the other case, so this is, oh dear, there's no way to write, no place to write it. Okay, so this is the case if x1 and x2 are independent. By which I mean linearly independent. It's just I didn't have room to write it. Okay, well, that's the end of, pretty much the end of the theory. And now let's start in on the matrices. The matrix, the basic new matrix we're going to be talking about this period and next one on Monday also, is the way that most people who work with systems actually look at the solutions to systems. So it's important you learn this word and this way of looking at it. What they do is look not at each solution separately, as we've been doing up till now. They put them all together in a single matrix, and it's the properties of that matrix that they study and try to do the calculations using. And that matrix is called a fundamental matrix. A fundamental matrix for the system. Sometimes people don't bother writing in the whole system. They just say it's a fundamental matrix for A, because after all, A is the only thing that's varying there. Once you know A, you know what the system is. All right, so what is this guy? Well, it's a 2-by-2 matrix, and it's the most harmless thing. It's the precursor of the Wronskian. It's what the Wronskian was before the determinant was taken. In other words, it's the matrix whose two columns are those two solutions. The only question is what we're going to call it. Okay, I have tried everything, and I've settled on calling it capital X because I think that's the one which leads to the, guides you in the calculations the best. So this is a definition too, so colon equality. What it is the matrix. Notice I'm not using vertical lines now because that would mean a determinant. It's the matrix whose columns are two independent solutions. Is that all? Yeah. You just put them side by side. Why? That will come out. Why should one do this? Well, first of all, in order not to interrupt the basic calculation that I want to make with this thing during the period, let's talk about that. It has two basic properties that we're going to need during this period. So these are the properties that are fundamental. Just two, and one is obvious, and the other you'll think, I hope, is a little less familiar, but I think you'll see there's nothing to it. It's just a way of talking, really. So the first is the one that's already in that theorem, embedded in the theorem, namely that the determinant of the fundamental matrix is not 0 for any t. Why? Well, I just told you it wasn't. This is the Wronskian. The Wronskian why is it never 0? Well, it's because I said these columns had to be independent solutions. So this is not 0, it's never 0. Never 0. It's not 0 for any value of t. Okay, that's good. As you'll see, we're going to need that property. But the other one is a little stranger, about which the only thing I can say is get used to it. Namely, that x prime equals ax. Now, why is that strange? That's not the same as this. This is a column vector. That's a square matrix. This is a column vector. This is not a column vector. This is a square matrix. This is what is called a matrix differential equation, where the variable is not a single x or a column vector of a set of x's like the x and the y. It is a whole matrix. Well, first of all, the thing first is, what is it saying? This is a 2 by 2 matrix. This is a 2 by 2 matrix. When I multiply them, I get a 2 by 2 matrix. What's this? This is a 2 by 2 matrix, every entry of which has been differentiated. That's what it means to put that prime there. To differentiate a matrix means nothing fancy. It just means differentiate every entry. It's just like to differentiate a vector x, y. To make a velocity vector, you differentiate the x and the y. Well, a column vector is a special kind of matrix. The definition applies to any matrix. Well, now, why is that so? Well, I state it as a property, but I'll continue it by giving you, so to speak, the proof of it. You'll see, in fact, there's nothing in this. It's nothing more than a little matrix calculation of the most primitive kind. Namely, what does this mean? Let's try to undo that. Well, what does the left-hand side really mean? Well, if that's what x means, the left-hand side must mean the derivative of the first column, that's its first column, and the derivative of the second column. That's what it means to differentiate the matrix X. You differentiate each column separately, and to differentiate the column means you differentiate every function in it. Well, what's the right-hand side mean? Well, I'm supposed to take A and multiply that by x1, x2. Now, I don't know how to prove this except ask you to think about it, or I could, write it all out here. But think of this as a bing, 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 okay? And this is a bing, bing. And this is a bong, bong, okay? All right. How do I do the multiplication? It goes, in other words, what's in the first column of the matrix? What's the first column? Well, it's da-da, and the lower thing is da-da. In other words, it is A times x1. Okay, shut your eyes and visualize it. Got it? Da, da, that's the top entry, and da, da, that's the bottom entry. It's like a ding, ding. It's what you get by multiplying A by the column vector x1. And the same way the other guy is, whoops, what you get by multiplying A by the column vector x2. So this is just matrix multiplication. That's the law of matrix multiplication. So matrix multiplication. That's how you multiply matrices. Well, good, but where does this get us? Well, you see from that what does it mean for those two guys to be equal? Well, that's going to happen if and only if x prime, x1 prime is equal to ax1. This guy equals that guy, and similarly for the x2s. So the end result is that this matrix, saying that the fundamental matrix satisfies this matrix differential equation, is only a way of saying in one breath that its two columns are both solutions to the original system. It's, so to speak, an efficient way of turning these two equations into a single equation by making a matrix. All right. I guess it's time finally to come to the topic of the lecture, which is I said the thing the matrices were going to be used for is solving inhomogeneous systems. So let's take a look at those. I thought I'd give you an example. So inhomogeneous systems. remember, essentially, what's one going to look like? So far, I mean, what we've done is, up to now, been solving, we spent essentially 2 weeks solving and plotting the solutions to homogeneous systems. There was nothing over there. And homogeneous systems, in fact, with constant coefficients. Stuff that looked like that we abbreviated with matrices. Now, to make the system inhomogeneous, what I do is add the extra term on the right-hand side, which is some function of t. Except since I'll have to have two functions of t because I have two equations. Now it's inhomogeneous, and what makes it inhomogeneous is the fact that these are not zero anymore. There's something there. Functions of t are there. So these are given functions of t, like exponentials, polynomials, you know, the usual stuff you have on the right-hand side of the differential equation. What's confusing here is that, you know, when you studied second-order equations, it was homogeneous if the right-hand side was zero, and if there was something else there, it was inhomogeneous. Unfortunately, I've stuck this stuff on the right-hand side, so it's not quite so clear anymore. You have to look for the, it's got to look like that, in other words. So how would the matrix abbreviation look? Well, the left-hand side is x prime. The homogeneous part is ax, just as it's always been. So the only extra part is the r. These two functions are, and I'll write them, since each of this is a column vector. After the multiplication, this is a column vector. What's left is a column vector. Now, explicitly, it's a function of t, given by explicit functions of t, like, again, like exponentials, or they could be fancy functions. So that's the thing we're trying to solve. Why don't I put it up in green? Our function. Our new and better and improved system. Well, think back to what we did when we studied inhomogeneous equations, when we were not talking about systems, but just a single equation. What we did was the main theorem, so I guess there are going to be 3 theorems today, not just 2. So theorem C, well, C, okay, C. Is that right? A, B, yes, A, B, we're up to C. Theorem C says, you write it yourself, says that the general solution, that's the general solution to the system, is equal to the complementary function, which is the general solution to x prime equals ax, the homogeneous equation, in other words, plus, what am I going to call it? xp, right you are, a particular solution. But the principle is the same. In other words, and it's proved exactly the same way. It's just linearity and superposition. The linearity of the system, original system, and the superposition principle. So the essence is that to solve this inhomogeneous system, what we have to do is find a particular solution. This part I already know how to do. We've been doing that for 2 weeks. The new thing is to find this. Now, if you remember back before spring break, that most of the work in solving the second-order equation was in finding that particular solution. You quickly enough learned how to solve the homogeneous equation, but there was no real general method for finding this. We had an exponential input theorem and with some modifications to it. We took a week's detour in Fourier series to see how to do it for periodic functions or functions defined on finite intervals. There were other techniques which I didn't get around to showing you, techniques involving undetermined method, so-called method of undetermined coefficients, although some of you peeked in your book and learned it from there. But the work is in finding xp. Now, the miracle that occurs here, by contrast, is that is that it turns out to be easy to find xp. And easy in this further sense that I don't have to restrict the kind of function I use. So that, for example, in the second homework problem I've given you, part 2, the second part 2 homework problem, you'll see how to use systems. For example, to solve this simple equation, I'll write it out for you. Consider that equation. Tangent t. Okay. What technique will you apply to solve that? In other words, suppose you wanted to find a particular solution to that. The right-hand side is not an exponential. It's not a polynomial. It's not like sine or cosine of bt. Could you use the Laplace transform? No, because you don't know how to take the Laplace transform of tangent t. Neither, for that matter, do I. Fourier series, not a good choice for a function which goes to infinity at pi over 2. So you can't do this until you do your homework. Now you'll be able to do it. Okay. So in other words, one of the big things is not only will I give you a formula for the xp, but that formula will work even for tangent t, any function at all. Okay. Well, I thought I would try to put a little meat on the bones of the inhomogeneous systems by actually giving you a physical problem so we'd actually be able to solve a physical problem instead of just, demonstrate a solution method. So here's a mixing problem. So mixing problem. Just to illustrate what makes a system of equations inhomogeneous. So here are two ugly tanks. Okay, I'm not going to draw these carefully, but they are both 1 liter. Okay? And they're connected by pipes, and I won't bother opening holes in them. So there's a pipe, so fluid's flowing back there, and here in this direction it's flowing this way. And but that's not the end. The end is there are stuff coming in to both of them, and I think I'll just make it coming out of this one. There's something realistic. So the numbers 2, 3, 2. Let's start there and see what the others have to be. So these are flow rates. So 1 liter tanks. The flow rates are in, let's say, liters per hour. And I have some dissolved substance in. So here is going to be X salt in there and some same chemical in there, whatever it is. So X is the amount of salt, let's say. Salt in tank 1. And Y, the same thing in tank 2. Now, if you've got stuff flowing unequally this way, you must have balance. Otherwise, you have to make sure that neither tank is getting emptied or bursting and exploding. So what's flowing in? What's X? 3 is going out. 2 is coming in. So this has to be 1 in order that the tank X stay full and not explode. And how about Y? 2 going, 3 coming in. So how much is going out? 2 there and 2 here. 4 is going out. 3 is coming in. So this also has to be 1. Those are just the flow rates of water or the liquid that's coming in. Now, the only thing I'm going to specify is the concentration of what's coming in. So here, the concentration is 5e to the minus t. And that's what makes the problem inhomogeneous. Here, the concentration is going to be 0. In other words, pure water is flowing in here to create the liquid balance. Here, on the other hand, salt solution is flowing in, but with a steadily declining concentration. Okay, so what's the system? What's the system? Well, it's you set it up exactly the way you did it when you studied first-order equations. In other words, it's inflow minus outflow. So it's outflow. So it's the out. What's the outflow? The outflow is all in this pipe at 3. So the flow rates are liters per hour. 3 liters per hour flowing out. How much salt does that represent? Well, that times the so it's -3 times the concentration of salt. But the concentration, notice, the concentration of X, the concentration equals X divided by 1. In other words, X represents both the concentration and the amount. So I don't have to distinguish. If I had made it 2-liter tanks, then I would have had to divide this by 2. So I'm cheating, but it's enough already. Okay. X prime equals minus 3x. That's what's going out. What's coming in? Well, 2y is coming in. Concentration here, what's coming in is at y, 2 liters, plus what's coming in from the outside. So we have to add that in, and that will be plus 5e to the negative t. How about y? Y prime is changing because of what comes in from x. That's 3x. What goes out? Now, what goes out? Well, 2 is leaving here, and 2 is leaving here. It doesn't matter that they're going out through separate pipes. They're both going out. So it's -4, 2 and 2. How about the inhomogeneous term? Well, there's 1 coming in, but there is no salt in it, and therefore that is not changing. What's coming in through that pipe is necessary for the liquid balance, but it has no effect whatever. I'll put a 0 here, but of course you don't have to put that in. Okay, this is now an inhomogeneous system. So in other words, the system is X prime equals this matrix, -3, the same sort of stuff we always had, plus the inhomogeneous term, which is 5, the column vector, 5e to the minus t, and 0. It's the presence of this term that makes the system inhomogeneous, and what that corresponds to is this little closed system being attacked from the outside by these external pipes, which are bringing salt in. Without those, of course, the balance would be all wrong. Now I'd have to change this to 3 and cut that out, I guess. But then it would be just a simple system, homogeneous system. It's these pipes that make it inhomogeneous. Okay, now I should start to solve that. But what I want to do, of course, is I did this just to illustrate where a system might come from. Before I solve that, what I want to do is, of course, solve it in general. In other words, how do you solve this in general? Because I promised you that you would be able to do in general, regardless of what sort of functions were in the R of t, that column vector. So let's do it. First of all, you have to learn the name of the method. This method is called, so it's a method to or for solving x prime equals ax, and it's a method for finding a particular solution. Of course, to actually solve it, then you have to add the complementary function. So we're looking for a particular solution to this system. Now, the whole cleverness of the method, which I think was discovered a couple of years ago by, I think, Legendre, I'm not sure. The method is called variation of parameters. I'm giving you that so that when you forget it, you'll be able to look it up at the index to some advanced engineering mathematics book or something, whatever's on your shelf. But of course, you won't remember the name either, so, so maybe this won't work. Variation of parameters. I'll explain to you why it's called that. All the cleverness is in the very first line. If you could remember the very first line, then I trust you to do the rest yourself. I don't know any motivation for this first step. But mathematics is supposed to be mysterious anyway. It keeps me eating. So XP, it says, look for a solution, and there will be one of the following form. Now, it will look exactly like, look carefully because it's going to be gone in a moment. It will look there. It will look exactly like this. But of course, it can't be this because this solves the homogeneous system. If I plug this in with these as constants, it cannot possibly be a particular solution to this because it will stop there and satisfy that with r equals 0. So the whole trick is you think of these as parameters which are now variable, as constants which are varying. That's why it's called variation of parameters. And you think of these, in other words, as functions of t. So we're going to look for a solution which has the form, since they're functions of t, I don't want to call them C1 and C2 anymore. I'll call them V because that's what most people call them. V or U sometimes. The method says, look for a solution of that form. So the variation of parameters, these are the parameters that are now varying instead of being constants. Now, if you take it in that form and start trying to substitute it into the equation, you're going to get a mess, and you won't be able. So I think I was wrong in saying I could trust you from this point on. I can only trust you. I'll take the first step from you, and then I can trust you to do the rest after that first step. Okay, the first step is to change the way this looks. Change the way it looks by using the fundamental matrix. Remember what the fundamental matrix was. Its entries were the two columns of solutions. Okay, so these are solutions to the homogeneous equation, the homogeneous system, and I'm going to write it using the fundamental matrix as, now think about it. The fundamental matrix has its columns x1 and x2. Your instinct might be using matrix multiplication to put the V1 and the V2 here, but that won't work. You have to put them here. This says the same thing as that. Let's just take a second out to calculate. So look, the x is going to look like x. I have no notation for this. Oh, yes, I do. So x1, y1, that's my first solution. My second solution, so here's the fundamental matrix, is x2, y2. And I'm multiplying this on the right by v1, v2. Doesn't it come out right? Look, what's the thing? The top is x1, v1 plus x2, v2. The top, x1, v1 plus x2, v2. It's in the wrong order, but multiplication is commutative, fortunately. And the same way, the bottom thing will be v1, y1 plus v2, y2. v1, y1 plus v2, y2. If I had written it on the other side instead, which is tempting because the v's occur on the left here, that won't work because what will I get? I'll get v1, x1 plus v2, y1, which is not at all what I want. You must put it on the right. But this is a very important thing. This is going to plague us on Monday, too. It must be written on the right and not on the left as a column vector. Okay? So the rest of the program is very simple. Substitute. I'll write it out as a program. Substitute into the system, into that, in other words, and see what v has to be. That's what we're looking for. We know what the x1 and the x2 are. It's a question of what those coefficients are and see what v is. Let's do it. I think. Okay, let's substitute. Let's see. So the system is x prime equals ax plus r. So I want to put in xp, this proposed particular solution. That's a fundamental matrix, and the v is unknown. Okay, how do I differentiate the product of two matrices? Look, you differentiate the product of two matrices using the product rule that you learned the first day of 1801. Trust me. Let's do it. So I'm going to substitute in. So in other words, here's my xp, and I'm going to write in what that is. So the left-hand side is the derivative of x prime times v plus x times the derivative of v. Notice that one of these is a column vector and the other is a square matrix. That's perfectly okay. Any two matrices which are the right shape so you can multiply them together, if you want to differentiate their product, in other words, if the entries are functions of t, it's the product rule. The derivative of this times this plus that times the derivative of this. You've got to keep them in the right order. You're not allowed to shuffle them around carelessly. Okay, so that's that. What's it equal to? Well, the right-hand side is a, and now I substitute just xp in, so that's x times v plus r. So is this progress? So what's v? Looks like a mess. But it's not. Why not? It's because this is not any old matrix X. This is a matrix whose columns are solutions to the system. And what does that do? That means x prime, it satisfies that matrix differential equation. X prime is the same as ax. X prime is the same as ax. And by a little miracle, the v is tagging along in both cases. So this cancels that. And now there is very little left. The conclusion, therefore, is that xv is equal to r. Okay, what's v? It's v that we're looking for, right? It's equal to. Okay, I have to solve a matrix equation now. This is a square matrix, so you have to do it by inverting the matrix, right? You don't just sloppily divide. You multiply on which side by what matrix? Choice of left or right. You multiply by the inverse matrix. On the left or on the right? Has to be on the left. Multiply both sides by x. Oh, I see. Multiply on the right. Yeah, okay. Ambiguous. Okay, multiply both sides of the equation by x inverse on the left, and then you'll get v is equal to x inverse r. Hey, how do I know that x inverse exists? Does x inverse exist? For a matrix inverse to exist, the matrix's determinant must be not 0. Why is this determinant of this not 0? Because its columns are independent solutions. Of course, this is not right. I forgot the prime here. Okay. I'm not failing this course after all. V prime equals that, so. This is done by differentiating each entry in the column vector, and therefore we should integrate it. So it'll be the integral, just the ordinary antiderivative of x inverse times r, and this is a column vector. The entries are functions of t. You simply integrate each of those functions in turn. So integrate each entry. And there's my V. And sorry, this is, you can't tell the V's from the R's here. And so finally the solution, the particular solution is XP, XP is equal to, it's really not bad at all. It's equal to X times V. It's equal to X times the integral of X inverse R dt. Now, actually, there isn't much work to doing that. Once you've got solved the homogeneous system and gotten the fundamental matrix, taking the inverse of a 2 by 2 matrix is almost trivial. You know, you flip those two and you change the signs of these two and you divide by the determinant and multiply it by R. And the hard part is if you can do the integration. If not, you just leave it the integral sign the way you've learned to do in this silly course, and you've still got the answer. So what about the arbitrary constant of integration? The answer is you don't need to put it in. Just find one particular solution is good enough. You don't have to put in the arbitrary constants of integration because they are already in the complementary function here. And therefore, you don't have to add them. I'm sorry I didn't get a chance to actually solve that. I'll have to let it go. The recitations will do it on Tuesday. We'll solve that particular problem, which means you will, in effect.